In this video, we're going to carry out what will hopefully be quite a simple exercise of assembling this circuit, which is a transistor amplifier, on a breadboard or a prototype board. And so this video is probably geared towards those who maybe are new to breadboarding and prototyping circuits, or maybe aren't so familiar with breadboards and how they work. But in this video, we're going to try and assemble this circuit here, which is an example of a Class A amplifier. And the reason that it's a Class A amplifier is it has this biasing stage here, which precedes the base or the input of our transistor. I don't want to talk too much about amplifiers and transistors and theory and that kind of thing in this video. I want to get on to the actual assembly in just a moment, but just very basic introduction to this biasing stage and what makes a Class A amplifier a Class A amplifier is that because the transistor is semiconducting, if we apply an AC input to this circuit here, which is the plan, the problem is that that AC input sort of centered about zero, if that's our sort of zero axis there, because the transistor is semiconducting in that it only conducts in one direction, the negative sort of half cycle of the waveform is going to be lost by the amplifier because the amplifier can only handle the forward bias component. So the purpose of this biasing stage here, which is just these two resistors basically forming a potential divider, is we're adding an additional voltage at this point here. So the input AC waveform has this DC voltage that's going to be added to it at this stage. And the reason for that is we can imagine that it lifts up this waveform. So rather than that waveform there being sort of set at about zero, that DC component is going to shift that waveform upwards so that it's always positive. And that means that the whole waveform is now interpretable by our transistor amplifier. We're not going to lose that half cycle that falls below zero or negative there. So that's the intention behind this video. And to do that, we're going to use a very simple, very small breadboard, like I mentioned at the beginning there, to assemble this circuit together. So just as a quick preamble here, we have a few resistors marked here, R1, R2, R3, and R4. There's a couple of changes I want to make to this schematic. This is one that I've just printed out, but R1 here, it says is a 30k resistor. I don't have any of those to hand. I'm going to replace that with a 33k resistor, but hopefully that won't make too much of a difference. The other change I'm going to make is we have a 12 volt DC power supply on the right hand side here. Well, I'm going to try and just use a very simple 9 volt battery there, and so rather than 12 volts we're going to have 9 volts instead. But other than that, this is hopefully what we're going to be building as it's printed out here. What we have on the right hand side here is our AC signal. We're going to supply a very small signal to this amplifier, and we'll be doing that in the next video. This video is really just about the assembly of this circuit. In the next video we'll actually start applying some inputs and taking some measurements and things like that. Okay, so to begin with, we've got our breadboard here, and the particular transistor that I'm using in this case is a BC108 transistor. Any NPN transistor will do for the purpose of most of these circuits, or any small sort of NPN bipolar transistor, but in this case I'm using the BC108. It looks something like this. It's got this sort of metal case, and it's got, though you might not be able to see in the video, it's got BC108 printed on it there. Now, I've looked up the data sheet for this particular transistor, and it's important, regardless of which transistor you'd use, that you look up the data sheet, which is usually just a case of Googling the code for it. And the reason I've done that is because we know that a transistor has three legs or three connections. We've got the base, we've got the base, we've got the collector, and we've got the emitter. So the base, on the left here, the collector at the top, the emitter at the bottom, as we draw it in a sort of schematic diagram like this. Now, the reason I mention this is because that order of the legs there doesn't always correspond with the order of the connections on the actual component. In this case with the BC108, however, it actually does. The BC108, if you have a look at the bottom there, I'm hoping you can see this in the video, but the three connections are kind of in this triangular arrangement. Now, bear in mind, I'm looking at this upside down. So from the top, if you imagine we've sort of got X-ray vision and we can look through the top there, what we're seeing is something that looks like that from the top down, if we imagine. And the legs are kind of arranged in this sort of triangular arrangement like so. And they do correspond with the collector, the base, and the emitter, just like the same sort of arrangement of the actual component in the diagram. That's not always the case. There's some weird models that for some reason have base, collector, emitter, or whatever in a different order. Ours correspond with what we kind of expect. Just remember that we're looking at that top down. Don't turn that upside down and associate the orientation with the connections looking from this side, because that's going to give us the wrong order. So looking that way, we've got these three connections here. And what I'm going to do is, with my breadboard, I'm going to put the transistor in first, because really the transistor is kind of like the core of this circuit. Everything else kind of connects to the transistor. So I want to get that sort of in situ in the first place. And the way that I'm going to do that is I'm going to have my collector, base, emitter in that order from left to right. So what I'm going to do is I'm going to just make a bit of a gap between these legs here, and I'm going to put those in 3 rows on just somewhere in the middle of my circuit there. So I've got there from left to right the collector, the base, the emitter. Now notice we've had a previous video on the sort of general principles of breadboarding, but they're in 3 separate rows so that they're not going to be short-circuited or connected to one another. Okay, so now that we're in place with the transistor, let's start seeing which other components we can start to connect quite easily. The first one is probably from the emitter to ground. Now I'm going to take the top rail and the bottom rail here as being our positive and negative connections, as in the diagram there. So that's the top rail of our breadboard, and that's the bottom rail of our breadboard, as you can imagine. So the emitter here is going from the emitter through this resistor R4 down to that bottom rail there, and that's a 1K resistor, as in our diagram. So I have here somewhere a 1K resistor, and that's going to go from the emitter. I'm actually just going to move that transistor up 1 just to give us a bit more room later on. From the emitter there, so it's in the same row as the emitter. Remember, we're collector, base, emitter. From the emitter down to the bottom rail there. That's our 1K resistor. So 1K, if you don't know your color codes, in this case for these 1/4 watt resistors, brown, black, red, and it's got a 5% tolerance, so gold on the end there. But brown, black, red is what we're looking for there for that 1K resistor. And similarly, from the collector, we've got a 10K resistor taking us from the collector to the top rail there. So same idea. I've got my collector, which was the first or the leftmost leg here as I've connected it. And that collector, we're taking that from that same row as the collector there up to the top rail there. I'm just going to bend that resistor slightly out of the way so it's not going to touch anything or cause any short circuits or connections that I don't want it to. Okay, so we've got R4, we've got R3 in place. Next, let's have a look at this biasing stage, because we have from the top rail R1, which connects to our base, and also connects to R2, which goes to our negative rail. So we can sort of compact this a little bit if we have a look at our circuit here. The base is the middle connection in our circuit. So R1 goes to the base, and we said that R1 is 33K. So here's our 33K resistor, which we said was R1 there. We changed that value. Orange, orange, orange in the color code there. And we said that's going from the top rail to the base. And so from the top rail, 33K, to the base, which is that middle connection there. So in that goes in the same row as that middle connection. So there's our 33K from the top rail down to the same row as the base, the middle connection of the transistor there. Okay, but from the base we have R2, which was a 3K9 resistor. So 3K9 is orange, white, red, if you can see that there, orange, white, red with a gold band tolerance. And that goes from the base to the bottom rail. So again, what we can do is from the base, which was the middle leg, to the bottom rail, we can have, if we can get it in there, we can have our 3K9. So again, it goes from the base, the middle leg of the transistor, to the bottom rail. What's left? Okay, so we have a couple of coupling capacitors on the input and what's going to be the output of this circuit. They're both 10 microfarads. I'm using these electrolytic capacitors, and what I want to do just in terms of their orientation, I'm going to have the positives innermost towards the circuit. And so with an electrolytic capacitor, generally one leg's shorter than the other, which we can see there. The longer leg's positive, the shorter leg's negative. But even if these legs are trimmed, generally these sort of these casings will have some kind of marking. In my case, there's this big sort of white stripe down one side, which isn't down the other side. We've got that white stripe there, which denotes the negative. And so we're having the positives innermost, which means the negative is going to be sort of outermost. And that connects to this point here in between R1 and R2. It also connects to the base. So all of these resistors here, R1, which was over here, R2 down here, these two connections here, and the base, well, anywhere in that sort of gap, I can have the positive connection of my coupling capacitor there. So I'm going to find a little space in that same row, if you can see there, is going just in between R2 and the base there. So in the same row, I've got R2 just below there. This is R2. In that tiny little gap there, I've got that positive leg of the capacitor. The negative leg, I'm just going to stick out in just some random row here. We're going to connect an input to it later. I'm just going to leave it sort of hanging there for now. But there's our input coupling capacitor. Similarly, we've got an output coupling capacitor here. And again, positive innermost, negative outermost. But that is going to be connected to this sort of point between R3 and the collector of our circuit there, of our transistor. And so R3 is all the way over here. It's the 10K resistor. And what I can do is I could put the output on this side as well. Else I'm going to start getting components sort of tangled and touching one another, which I don't really want. What I'm going to do, rather than put the output on this side as well, which might be a bit confusing when you've got the input and the output capacitors on the same side of the circuit, I'm going to cheat a little bit. I'm just going to use a wire link here. I'm going to take that point where I would have connected the positive of the capacitor between R3 and the collector, which in my case, the most sort of suitable point is probably there. So there's R3 and the collector's the leftmost leg. I've got a tiny gap in between. I'm going to put, if I can get it in, I'm going to put a little link right in there between the two. I hope you can see that. But there's the leftmost leg of the transistor. R3 was in the same row, but I've just sort of put this link in between the two. And the reason I'm doing that, I'm just buying myself a little bit of space here. I'm going to take that away just to the side there. And from that, I'm going to connect in the same row the positive leg of the capacitor and the negative outermost there. So just to make it resemble a little bit more the layout of the schematic there, and it just sort of buys a little bit of space there. It's a good idea, whilst we're on the topic, just to make sure that no components are accidentally touching one another that shouldn't be. If you've got the space to do so, it's a good idea to sort of just bend a little bit of space between components to make sure that they've got room and whatnot. Okay, last thing I think that we've still got to do is just one more capacitor here. This is an example of a bypass capacitor in a circuit, and it's in parallel with R4. So R4 was our 1K resistor. There it is there. Basically, I want a capacitor that's in parallel with this resistor. So here's my 33 nanofarad capacitor. It's not an electrolytic capacitor, it's a polyester capacitor, and these can be connected either way around, and so it doesn't really matter which way I connect this. Another thing I'll just mention while I'm on the topic, you can see here I'm just trying to scrape off a little bit of glue. When these components are shipped, they're sort of all glued together by the ends of the legs, and so if there's some residual sort of glue that's on the end of these legs, it can sort of act as an insulator when you put it into the breadboard. So it's a good idea just to visually check and make sure. Usually you can just scrape it off with your nail, but make sure that those components are sort of clear of any sort of residue. Anyway, we want that capacitor in parallel with this resistor. There's our capacitor. And so here's R4, that 1K resistor on our breadboard here. What I'm going to do, because the legs of the resistor generally are slightly longer than the legs of the capacitor, I'm going to borrow some space here. If we can see, R4 connects to that hole there. I'm just going to use the next one up, basically, just so that the resistor is long enough to stretch that far, but the capacitor might not be. And then in the hole that was below, where I've just moved it out of, in the same row as where that resistor is connected, where it just was connected, I'm going to connect my capacitor there. So there it is, in the same row, in fact in the socket that just occupied, in the same row as R4 there, that 1K resistor. Just below, in the same row, I've got that 33 nanofarad capacitor. Now that 33 nanofarad capacitor connects down here below the resistor, but to be honest, it connects basically to that bottom rail anyway. So anywhere on this bottom rail, I can connect the capacitor. It doesn't really matter. And so we'll try and, if we can, get him in there. So there he is in the bottom row. So I think, let's just do another quick check. I think that's everything. In the next video, we'll be actually connecting some inputs and taking some measurements. One thing I should say, sorry, an obvious one, I should mention the power supply very quickly. I'm just using a battery snap like this for a 9-volt battery. And so we said that the top rail corresponds with the sort of top rail on the schematic there. And so anywhere on that top rail, I can connect the battery snap or the red positive connection from that battery snap. And likewise, the bottom rail corresponds with the bottom of our schematic. And there's our battery snap waiting for a battery there. So obviously, if I do sort of connect a battery, nothing much happens. But what we're going to do in the next video is we're going to apply a small signal input to the input here, and we're also going to take measurements of the input and the output and sort of compare the two and see them visually. And we're going to do that using oscilloscope software on the computer. So I hope you found this video useful to assemble this circuit here, but if you follow us along for the next video, we'll be using this exact same circuit and looking at what it does.